Alright, we are back today and we are going to get into equilibrium concentration of vacancies, how to kind of approach it, and reading these Arrhenius relationships. So let's go ahead and I'm going to clear up let's clear up, let's go to our draw, let's erase this function. So let's see what we've got again to work with. So my equilibrium concentration of vacancies is this XV. It's the total number of vacancies n divided by total number of sites. Total number of sites. And we can see here that typically for metals, we could approximate this entropy of vibrational entropy is equal to 1. It's exponential. So this equals 1. And now what we're left with is just equilibrium concentration of vacancies, exponential minus delta HF divided by KT. So let's go ahead and let's plot this, or let's kind of calculate some values in Mathematica. So this is my expression. So XV equals exponential minus minus del HF divided by K times T. Oops, T. So that's my expression. K, my Boltzmann's constant, it could be 1.38 times 10 to the minus 23 or 8.617 times 10 to the minus 5. And that is in joules per, or actually EV per K, EV per Kelvin. So let's go ahead and that. So that is going to be my Boltzmann's constant there. So I could do a couple things now. So let's say that my delta H formation, del HF is 2, for example. 2 electron volts. Let's go ahead and comment this out. Electron volts. Here, 2 electron volts. Well, I could plot now XV as a function from basically going from, as a function of T, goes from 0 to, let's say, 1,000 K. And lo and behold, I get an exponential kind of function here. I could also do XV slash dot T goes to, let's say, at room temperature, 298. This would be my number of vacancies in my system. So 10 to the minus 34. Not many vacancies because, again, we're at low temperatures. But look what happens if I go to 500. Look at that, 13 order of magnitude change, even though we just increased our temperature by 200 degrees. So again, this is the power of that exponential relationship, that Arrhenius relationship. So that's kind of one of the key things that you want to kind of basically consider and think about as you're going through this problem. Now, let's go back to our function here. Oftentimes, we want to express our function kind of a little bit differently. So we want to actually plot the log of x of v, because we know that xv equals exponential minus delta hf divided by kt. If I take the natural log, you can see I could rewrite this as a linear function. Log of xv minus delta hf as my slope here. So this is equal to my slope. I know what k is, and then I can figure out what is my delta hf. So for example, in this graph, let's say minus 20 at 0.002, and then I have basically, let's say that's like minus 100. So let's go ahead, let's kind of calculate the slope here. So let's say I have this this height at this distance here. Let's go ahead and draw. It's a little bit hard to kind of read. So this looks like 90. Let's just say this is 90. So this is minus 90, and it's 0.1. So the rise would be, let's see, we'd go minus 70, right? So over the run, which would be 0.01 minus 0.002. And now we can go ahead and solve for that particular example. So solve when minus 70 divided by, what is it, 0.01 minus 0.002. So that's my slope. Set that equal to del HF unknown divided by K, del HF, and so let's set that del equal del HFN. And this would be our slope, minus 0.75 electron volts. So there it is. That would be essentially our kind of value, or not minus 0.7. It'd be just that kind of value here, because again, the slope is actually going to be negative because of the rise over the run. So actually kind of plug that in. Anyways, kind of that's going to be the difference there. So that would be our delta HF of fusion. So that would be how you kind of plot this. Now you could also, let's go ahead and let's say, for example, I created y values of, or actually y ln xv. And I do a table of natural log of xv, and then I'm going to do from, let's go slash dot, let's go from t. So I'm going to plug in t goes to I. So I'm going to do this from I from basically 1 to 1,000. I'm going to do this. It'd be quite a few numbers. So let's go ahead and we'll just call it. Yeah, let's just keep it there. So this would be my y values. And I could also do my x values, the 1 over t. So x vals, x1 divided by t, 1 over t. So I could just do here 1 divided by I for my time values, or my temperature values, excuse me. And it's just going to be this. So I can now do, I can do a list line plot, transpose, x1 over t, y ln of v. This is probably not the most elegant way to do it, but it'll work nonetheless. And what do you know? So if I were to take again, let's go ahead and get the coordinates. Let's get my slope here. Let's get my slope here. Control C. So let's look at here. I could take differences all 2. So this is taking the differences of my run divided by my rise. So that's my slope here. So now I just do, again, solve. My slope is equal to this, set equal to del H fun divided by K, solve for del H fun. And pretty close. Look at my delta H diffusion is 2 here, and there we go. And then this is, I think this is a minus. That's why I keep getting these values a little bit off. That's where we're going here. But there you go. Again, those are kind of the values that you'll get. So that's how you can hopefully help and solve some of those problem set questions. So hopefully that addresses some of the issues with basically our Arrhenius relationships. Thanks. Have a good one. Bye.